There is plutonium on the floor of the Pacific Ocean. Not the kind humans made, the kind that should not exist on this planet at all. Because every atom of it, from Earth's formation, decayed away billions of years ago. A physicist in Australia counted the atoms one by one in weeks of accelerator time and confirmed they came from space. That was published in Science in 2021. Nobody talked about it. Separately, there is an extinction event at the boundary between the Pliocene and the Pleistocene, roughly 2.5 million years ago, that wiped out 55% of marine mammal genera, 43% of sea turtles, and some of the largest predators the ocean has ever produced. The kill pattern is specific. It targeted the biggest animals first, and the mechanism that best explains that selectivity is one that no geology textbook mentions, because it did not come from Earth. And then there is the fact that your solar system is right now sitting inside a cavity in the galaxy roughly 1,000 light years across, carved by 15 stars that exploded over the past 14 million years. You have been inside this structure your whole life. The sun drifted into it 5 million years ago by accident. Those three things are the same story. And by the time you see how a chunk of rock from the bottom of the ocean connects to Apollo moon samples from 1969, to a radiation model that puts muons a kilometre deep in the water column, to iron 60 falling on Antarctic ice this year, the part about the plutonium will be the least disturbing thing you heard tonight. So, settle in, get comfortable, subscribe if you have not already. If you want to go deeper on topics like this, space, physics, deep time, the things that reshape how you think about where you actually live, I do broader explorations of all of it over on Patreon. Stay to the end of this one, because the last 20 minutes are where the story stops being about the past and starts being about right now. Let's start where it started. Right now, as you are listening to this, radioactive iron from a dead star is falling on Antarctica. Not figuratively, not as a metaphor. Actual atoms of iron 60, forged in the core of a star that no longer exists, are settling onto the ice sheet at the bottom of the world at this moment. They were detected in fresh Antarctic snow in 2026 by a team at the Helmholtz Center in Dresden, using an accelerator sensitive enough to count individual atoms. And the fact that you have never heard about this, that this was not on the front page of every newspaper on the planet, tells you something important about the story I am about to tell you. Because this is not new. This is not a recent discovery. The first evidence that dead stars have been depositing radioactive debris onto Earth was published in 1999 in Physical Review Letters by a team at the Technical University of Munich. And the implications of what they found should have changed the way you think about where you live. Not your city, not your country, where you live in the galaxy, what the neighborhood is actually like, and what it has been doing to you. I spent an unreasonable amount of time reading the primary literature on this. Papers in Nature, papers in Science, papers in the Astrophysical Journal Letters, and the proceedings of the National Academy of Sciences. And what I found is a story that connects a chunk of rock dredged from the bottom of the Pacific Ocean to the extinction of the largest predator that ever lived, to a 1,000 light-year cavity blown open by 15 dead stars surrounding our solar system right now, to plutonium atoms that have no business existing on this planet, and ultimately to the question of whether the galaxy itself has been shaping the trajectory of life on Earth in ways that nobody wanted to talk about publicly. And I mean nobody. The papers exist, the data is confirmed, and the silence around the implications is deafening. Here is what happened. In 1999, a physicist named Klaus Knie was working at the Meyer-Leibniz laboratory in Garching, just outside Munich. Knie was not famous. He was not chasing headlines. He was running samples through a tandem accelerator, which is a machine that strips electrons from atoms, accelerates them to a significant fraction of the speed of light, and then sorts them by mass with enough precision to identify individual isotopes in a sample that might contain only a handful of the atoms you are looking for. This is called accelerator mass spectrometry, and in the late 1990s, it was one of the only techniques on Earth sensitive enough to find what Knie was looking for. What he was looking for was iron-60. Iron-60 is a radioactive isotope of iron. It has a half-life of 2.62 million years, plus or minus 40,000 years. That number was pinned down by Rugel and colleagues in 2009, published in Physical Review Letters, Volume 103. Before that, the accepted half-life was 1.49 million years, which is a significant difference and one that matters for everything that follows. But here is the key thing about iron-60. It is not produced naturally on Earth. It is not produced by any geological process. It is not produced by cosmic ray spallation in any meaningful quantity. It is produced almost exclusively in one place: the interior of a massive star, in the helium shell and oxygen neon-burning layers, during the final stages before that star explodes. When a massive star goes supernova, it ejects iron-60 into the interstellar medium. Some of that debris, if the star is close enough, will eventually reach our solar system, drift down through Earth's atmosphere, and settle onto whatever surface is available: land, ocean, ice, the moon. And because iron-60 has a half-life of 2.62 million years, every atom of iron-60 that was present when the Earth formed 4.56 billion years ago has long since decayed into nickel, 60, and cobalt 60. It is gone. It has been gone for billions of years, which means that if you find iron-60 anywhere on Earth today, it did not come from here. It came from a dead star, and Knie found it in a ferromanganese crust that had been pulled from the floor of the Pacific Ocean. These crusts grow at almost unimaginably slow rates, roughly 2 to 3 millimeters per million years. A crust 10 millimeters thick has been accumulating for roughly 4 million years, and because they grow so slowly, each layer is a chronological record. Deeper layers are older, surface layers are younger. You can slice them and date them, and whatever atoms settled onto the ocean floor during each time period are locked in the corresponding layer like a geological filing cabinet. Knie sliced the crust into layers. He dissolved them. He chemically separated the iron. He loaded the iron onto sample holders and fed them into the tandem accelerator at Garching. And in the layer corresponding to roughly 0 to 2.8 million years ago, he found a signal: iron-60. Not much of it. The iron-60 to iron-56 ratio was on the order of 10 to the negative 15. That is a few atoms of iron-60 for every quadrillion atoms of normal iron. And I want you to sit with that number for a moment, because it is important for understanding what kind of science this is. We are not talking about finding a needle in a haystack. We are talking about finding a specific needle in a haystack, the size of a country. And Knie found it. The paper was published in 1999. Knie, Korschenek, Festerman, Wallner, Scholten, and Hillebrand. Indication for supernova produced iron-60 activity on Earth. Physical Review Letters, Volume 83, pages 18 through 21. Think about that title for a moment. Indication for supernova produced activity on Earth. That is a physicist telling you, in the measured, careful language of a peer-reviewed journal, that a star exploded near enough to Earth that its radioactive debris physically landed here, and you can hold it. Knie himself said it. I found the quote in a Nautilus piece that profiled the early work. He said, and I am paraphrasing his published remarks, "We are part of the universe, and we have the chance to hold the astrophysical matter in our hand if we look at the right places." That is the kind of sentence that sounds almost banal until you really hear it. You can hold the debris of a dead star. It is sitting in the geological record. It has been there for millions of years, and nobody told you about it. But 1999 was just the indication. The signal was there, but it was broad. The time resolution was limited. Knie knew there was iron 60 in the crust, but he could not pinpoint exactly when it had arrived. The crust layers were thick enough that the signal could have come from any time within a multi-million-year window. To make this story airtight, he needed better resolution. So he went back. He went back to the same accelerator, the same laboratory in Garching, and he sliced the crust thinner. 28 layers this time, each layer corresponding to a narrower time window. And this time, in 2004, he got the answer. The iron 60 was not spread evenly across millions of years. It was concentrated in a peak, a sharp, unmistakable spike, centered at approximately 2.8 million years ago. Published in Physical Review Letters again. Volume 93, Article 171, 103, 2004. The authors wrote that the signal was consistent with a supernova at a distance of, quote, a few tens of parsecs, end quote. A parsec is 3.26 light years. A few tens of parsecs means somewhere between about 60 and 300 light years away. That is staggeringly close by astronomical standards. That is our neighborhood. And here is the thing that should stop you cold. 2.8 million years ago is not some arbitrary date in deep time. It is the boundary between the Pliocene and the Pleistocene. It is the moment when Earth's climate shifted dramatically, when glaciation in the northern hemisphere began in earnest, when the African landscape dried out and opened up, creating the savannas that pressured a certain line of primates to stand upright and start walking. 2.8 million years ago is the hinge point of the world you live in, and a star exploded within a few hundred light years of Earth, right at that moment. That could be a coincidence. It could be. But the question of whether it is a coincidence is one of the most important questions in modern astrophysics, and it is one that very few people, outside of a handful of specialist departments, are even aware is being asked. I need to pause here because I promised you a story about the ocean floor and the extinction of the largest predator that ever lived, and plutonium that should not exist, and a cavity surrounding your solar system. Right now, and I have given you exactly one physicist and one chunk of Pacific crust. But the reason I am spending this much time on Knie is that what he started in 1999 became one of the most quietly consequential threads in modern science. And the word quietly is doing an enormous amount of work in that sentence. Because after Knie published, the story should have exploded. A radioactive fingerprint of a dead star, physically present in Earth's geological record, time-stamped to one of the most dramatic climate transitions in the history of life. That is not a footnote. That is not an incremental advance. That is a paper that should have changed how we teach the history of our planet. It did not. The paper was cited by specialists. It was known in the accelerator mass spectrometry community and among nuclear astrophysicists, but it did not cross over. It did not reach the public. It did not reach textbooks. And I want to be precise about why, because this is not a conspiracy. Nobody suppressed Knie's work. Nobody told him to be quiet. What happened is something more mundane and in some ways more damaging. The result was too weird for any single discipline to claim. It sat at the intersection of nuclear physics, astrophysics, oceanography, and paleoclimatology. It did not belong cleanly to any department. And in modern science, results that do not belong cleanly to any department tend to fall into the cracks between them. Not because anyone decides they are not important, but because no one's career depends on promoting them. That changed in 2016, and it changed because of a man named Anton Wallner. Wallner is Austrian. He trained at the University of Vienna, earned his doctorate working on aluminum-26, another radionuclide used to trace astrophysical processes. His early career took him through the Vera laboratory in Vienna, which is one of Europe's premier accelerator mass spectrometry facilities, then to ANSTO in Sydney, and eventually to the Australian National University's Department of Nuclear Physics in Canberra. By the time he turned his attention to iron-60, he had spent more than a decade perfecting the art of counting atoms that barely exist. And I mean that literally. Wallner described the detection process in terms that should give you a sense of just how painstaking this work is. He said detection rates were, quote, about 1 iron-60 detection every hour or 2, end quote, requiring, quote, many weeks of heavily booked accelerator beam time, end quote. Imagine that, weeks of sitting in front of an accelerator, waiting for a single atom of iron-60 to reveal itself. Then another hour. Then another atom. And you need enough atoms to build a statistical signal that can survive peer review at Nature. That is the kind of science where patience is not a virtue. It is the entire methodology. What Wallner did that Knie could not was go global. Instead of a single Pacific crust, Wallner assembled a collection that spanned the planet. 4 deep-sea sediment cores from the Indian and Southern Oceans, recovered from the research vessel El Tanin. 2 ferromanganese crusts from the Pacific, 2 ferromanganese nodules from the Atlantic. 8 samples from 3 oceans. If the iron-60 signal was real, if it genuinely came from a supernova whose debris blanketed the inner solar system, then it should appear everywhere, not just in one crust from one location on one ocean floor, everywhere. It did. The paper landed in Nature on April 6, 2016. Wallner, Feige, Kinoshita, Paul, Fifield, Golser, Honda, Lineman, Matsuzaki, Merchel, Rugel, Timms, Steyer, Yamagata, and Winkler, recent near-Earth supernovae probed by global deposition of interstellar radioactive iron-60. Nature, Volume 532, pages 69 through 72. The results confirmed everything Knie had found and then revealed something he had missed. There was not one signal. There were 2. The first pulse of iron, 60, the one Knie had already identified, spanned from 1.7 to 3.2 million years ago. In the El Tanin sediment cores alone, Wallner's team detected 288 atoms of iron, 60, in that time window. The concentration was approximately 6.7 times 10 to the 4th atoms per gram of iron. That is vanishingly small. But it was there, in every ocean they checked. The second pulse was older, 6.5 to 8.7 million years ago, visible in the deeper layers of the Pacific crust, less well resolved because the deeper you go in these records, the more the time resolution degrades. But unmistakable. 2 separate events, 2 stars that died close enough to Earth that their radioactive ejecta physically reached us. And Wallner said something in the press coverage that stuck with me. He said, quote, "It suggests there were a series of supernovae, one after another. It is an interesting coincidence that they correspond with when the Earth cooled and moved from the Pliocene into the Pleistocene period. End quote. An interesting coincidence. That is a scientist being careful. That is a scientist hedging. But read between those words and you can hear what he is actually saying. 2 nearby supernovae. 2 major transitions in Earth's climate history. And he used the word coincidence in a tone that very clearly means he does not think it is one. But the 2016 Nature paper did something else that matters enormously for this story. It established that the Iron 60 signal was not a spike. It was not a single sharp event. It was spread across roughly 1 million years for each pulse. That tells you something critical about the delivery mechanism. A single supernova explosion takes a matter of seconds. The light reaches Earth in decades to centuries, depending on distance. But the debris, the heavy atoms, the iron and nickel and heavier elements, those travel much more slowly. They are swept up in the expanding shockwave of the supernova remnant, caught in magnetic fields, deflected and scattered by interstellar dust. They arrive not as a bullet, but as a long, slow rain. And that rain for the younger event lasted from roughly 3.2 million years ago to 1.7 million years ago. 1.5 million years of stellar debris falling on this planet. And now I need to tell you about the moon, because the ocean floor has a problem as a recording medium. Biological uptake varies, sedimentation rates change, chemical weathering alters the record. Ferromanganese crusts are good, but they are not perfect. If you want a clean record of what has been falling on the inner solar system from space, you want a surface with no atmosphere, no biology, no water, no weathering. You want the moon. In 2016, the same year Warner's Nature paper was published, a team including several of the original Munich group published a companion result. Fimiani, Cook, Festerman, Knie himself, Korschinek, and others. Interstellar Iron 60 on the surface of the moon. Physical Review Letters, Volume 116, Article 1, 104. They had obtained lunar soil samples from Apollo 12, Apollo 15, and Apollo 16 through NASA's CAPTEM program, the curation office that manages access to the irreplaceable samples brought back between 1969 and 1972. They dissolved the lunar regolith, they extracted the iron, they loaded it into the accelerator at Garching. And the Iron 60 was there. On the moon, the Iron 60 to Iron 56 ratio was roughly 10 times background, far more than cosmic ray spallation could produce. Gunther Korschinek, who had been Knie's mentor in the original 99 experiment, said the measured Iron 60 flow, quote, corresponds to a supernova at a distance of about 300 light years, end quote. Think about that for a moment. Lunar soil, collected by American astronauts in the late 1960s and early 1970s, locked away in nitrogen-purged vaults in Houston for half a century, opened and analyzed, and found to contain the radioactive remains of a star that died before the genus Homo existed. The debris was there the whole time. In a sample that Alan Bean drove into the lunar surface, with a hammer on the Apollo 12 mission in November of 1969, nobody knew what they were carrying. And I need you to keep holding 2 threads here, because they are about to converge in a way that changes the scale of this entire story. Thread 1 is the Iron 60. It is confirmed. It is global. It is on the moon. 2 nearby supernovae deposited their debris on Earth. One roughly 2.5 million years ago, and one roughly 7 million years ago. Thread 2 is the question of what that debris represents. Not what it is, but what it did. Because Iron 60 does not arrive alone. When a star explodes, the Iron 60 is a tracer. It is the fingerprint you can detect millions of years later. But the immediate aftermath of a nearby supernova is not a gentle rain of exotic isotopes. It is a catastrophe. And here is where it gets worse. In 2017, a physicist at the University of Kansas named Adrian Melott published a paper that took the Iron 60 data and asked the question that the nuclear physicists and oceanographers had been carefully avoiding. Not where did the supernova debris come from? Not when did it arrive, but what did it do to life on Earth when it got here? Melott is an interesting figure in this story. He trained as a cosmologist. His early work was in large-scale structure, the distribution of galaxies in the universe. Somewhere along the way, he pivoted toward what he calls astrobiophysics, which is exactly what it sounds like, the study of how astrophysical events affect biology. He runs the Astrophysics Biology Working Group at the University of Kansas. It is funded by NASA's exobiology program, and the papers he has produced over the past decade are some of the most uncomfortable reading in modern science. Melott and his frequent collaborator Brian Thomas, an atmospheric chemist at Washburn University, built detailed models of what happens to Earth's atmosphere when a supernova detonates at various distances. The key variable is cosmic rays. A supernova produces an enormous flux of high-energy particles, primarily protons, that are accelerated in the expanding shock wave. If the supernova is close enough, say within about 50 parsecs or roughly 160 light-years, those cosmic rays arrive at Earth in sufficient numbers to wreak havoc on the upper atmosphere. Here is what their models show. At 50 parsecs, a core collapse supernova strips between 15 and 40% of the ozone column, depending on latitude. That is not a gentle thinning. That is a hole. And when the ozone drops, ultraviolet B radiation at the surface rises by roughly 50%. UVB is the wavelength range that causes DNA damage, cataracts, skin cancer, suppressed immune systems, and disrupted photosynthesis in phytoplankton. A 50% increase in UVB sustained over thousands of years would be an environmental disaster of the first order. But the ozone is not even the main event. The main event is the muons. When high-energy cosmic ray protons hit the upper atmosphere, they create a shower of secondary particles. Among the most penetrating of these are muons. Muons are heavy cousins of electrons. They carry a charge, they interact with matter, and they are extraordinarily good at passing through things. Muons pass through rock. They pass through water. They pass through you. In fact, roughly 10,000 muons are passing through your body every minute right now as you listen to this. That is the normal background rate from ordinary cosmic rays. Melott's 2017 paper, published in the Astrophysical Journal, calculated that a supernova at 50 parsecs would increase the ground level muon dose by a factor of roughly 150. Some scenarios pushed it to 2,000. And here is the detail that made my stomach drop when I read it. Muons penetrate water. They penetrate deep water. The elevated muon flux would irradiate the ocean to depths approaching 1 kilometre. A kilometre beneath the surface, where the sunlight cannot reach and the ozone layer is irrelevant, where the largest marine animals live and migrate and breed. And the radiation dose scales with body size. Larger organisms absorb more muons per unit time simply because there is more of them to hit, which means the animals most vulnerable to supernova-induced muon radiation are exactly the ones you would predict if you were looking for a kill mechanism that selectively targets large marine life. Animals like the giant sea turtles that were among the most diverse marine reptile groups of the Pliocene. Animals like the enormous filter-feeding whales that were filling ecological niches created by the closure of the Central American Seaway, and animals like Otodus Megalodon. Megalodon, the largest predatory shark that ever lived. Estimates put it at 15 to 18 meters long, 50 to 60 feet, with jaws that could open wide enough to engulf a small car and a bite force that has been modeled at over 108,000 newtons. For comparison, the great white shark bites at roughly 18,000 newtons. Megalodon was 6 times more powerful. It was the apex predator of the Pliocene Ocean, and it vanished. Now I need to be precise here, because the timing matters, and the timing is contested. For years, the conventional dating for Megalodon's extinction was around 2.6 million years ago, right at the Plio-Pleistocene boundary, which lined up almost too perfectly with the Iron 60 signal at 2.5 to 2.8 million years ago. But in 2019, a paper by Bosenecker and colleagues in PeerJ redated Megalodon's last confirmed occurrence using optimal linear estimation and pushed it back to roughly 3.51 million years ago. That is about 1 million years before the peak of the Iron 60 signal. This matters because it weakens the direct causal link between supernova radiation and Megalodon's specific extinction. But it does not weaken the broader story because Megalodon was just one species in a catastrophe that was much, much larger. In 2017, a paper by Pimento and colleagues in Nature Ecology and Evolution documented something that the paleontological community had not fully grappled with: a marine megafauna extinction at the Plio-Pleistocene boundary that was far more severe than anyone had previously recognized. At the genus level, marine mammals lost 55% of their generic diversity. Sea turtles lost 43%. Seabirds lost 35%. Sharks lost 9%. Entire ecological roles were erased. The giant filter-feeding cetaceans that had dominated the Pliocene oceans were decimated. Sea cow diversity collapsed. The marine food web was restructured from the top down. And the timing of this extinction, unlike Megalodon's individual disappearance, lines up with the Iron 60 signal with uncomfortable precision. The Plio-Pleistocene boundary is conventionally placed at 2.58 million years ago. The Iron 60 peak in Wallner's data is centered at roughly 2.5 to 2.8 million years ago. The overlap is not perfect, but it is close enough that Melott, working with Marino and Paolucci, published a paper in Astrobiology in 2018 that made the argument explicit. They wrote, and I want you to hear the measured language of a peer-reviewed paper making an extraordinary claim. Quote, "It is reasonable to hypothesize that this increase in radiation load may have contributed to a newly documented marine megafaunal extinction at that time." End quote. Reasonable to hypothesize. May have contributed. This is the language of scientists being careful. This is the language of people who know that correlation is not causation, and who are hedging accordingly. But read the data behind those careful words. A supernova detonated within a couple hundred light years of Earth. Cosmic rays flooded the atmosphere. Muon radiation increased by a factor of 150 or more. That radiation penetrated a kilometre into the ocean. A third of large marine animal genera vanished. And the Iron 60 that proves the supernova happened is sitting right there in the geological layer that corresponds to the extinction. That should have been front-page news. Every newspaper on the planet. A star exploded near Earth, and it may have helped kill off the largest animals in the ocean. And I do not mean helped in a minor way. I mean the modeled radiation dose at ocean depths of a few hundred meters exceeded the total present-day surface radiation from all sources. For roughly 100,000 years, this was not a flash. This was not a brief event. The cosmic ray bombardment lasted 100,000 years because, And this is a detail I am going to come back to because it is critical. The particles were being reflected. Something was bouncing them back. The cosmic rays hit Earth, passed through, should have continued on into deep space. And instead, they came back, again and again, for 100 millennia. And the thing that was bouncing them back is the same thing that makes this entire story so much bigger than one dead star and one dead shark. But I am going to hold that thread for a moment, because before I can explain what was trapping the cosmic rays, I need to tell you about the part of this story that genuinely keeps me up at night. The part that has nothing to do with Iron 60, and everything to do with an element that should not be on this planet at all. Plutonium-244. In 2021, Anton Wallner published again, this time not in Nature, but in Science, which, if anything, is a more conservative journal. Wallner, Froelich, Fifield, Golser, Hotchkiss, Kinoshita, Paul, Marchkini, Pavetic, Timms, and Wallner again. Iron 60 and plutonium-244 deposited on Earth constrain the R process yields of recent nearby supernovae. Science, Volume 372, pages 742 through 745, May 14th, 2021. Read that title again, Iron 60 and Plutonium-244. Wallner did not just find more iron from a dead star. He found plutonium from space, on the ocean floor, in the same geological layers. Plutonium-244 has a half-life of 80.6 million years. That is long by human standards, but short by the standards of Earth's history. The solar system formed 4.56 billion years ago. That is roughly 57 half-lives of plutonium-244, which means that any plutonium-244 that was present when Earth formed has decayed away so thoroughly that there should not be a single atom of it left on this planet. Not one. All the naturally occurring plutonium-244 is gone, has been gone for billions of years. And Wallner found it, a few dozen atoms, pulled from a Pacific Ocean ferromanganese crust recovered from approximately 1,500 meters depth, detected using accelerator mass spectrometry at the Ansto Vega Accelerator in Sydney. A few dozen atoms of an element that has no business being here. And I need you to understand how small that number is. A few dozen atoms in a sample of ocean crust. Wallner was not finding grams of plutonium or milligrams or micrograms. He was finding individual atoms, counting them one by one. In weeks of accelerator beam time, the sensitivity required to do this is almost beyond comprehension. You are looking for a handful of atoms of a specific isotope in a chunk of rock, and those atoms are mixed in with trillions upon trillions of other atoms. And you need to find them, identify them, count them, and determine which geological layer they came from, so you can figure out when they arrived. He did it, and the plutonium-244 was there in the same time windows as the Iron 60, both at 2.5 million years ago and at 6 to 7 million years ago. The same two pulses, the same two events. But here is where the plutonium takes the story somewhere the iron alone could not go. Iron 60 is produced in supernovae. That much is straightforward. It is made in the shells of massive stars and ejected when those stars explode. But plutonium-244 is different. Plutonium-244 is produced by something called the rapid neutron capture process, the R process. And the R process only happens in the most violent events in the universe. For decades, the primary candidate for the R process was the core collapse supernova itself. The idea was that in the unimaginable conditions at the heart of a collapsing star, neutron densities could become high enough and temperatures extreme enough to drive rapid neutron capture, building elements all the way up the periodic table to uranium and plutonium and beyond. That was the standard story. Supernovae make iron-60 and also make plutonium-244, and both end up in the ejector. But Wallner's 2021 result threw a wrench into that story because he measured the ratio of plutonium-244 to iron-60 in the ocean crust samples, and the ratio was wrong. It was lower than supernova models predicted. If supernovae were the sole source of both isotopes, you would expect a certain ratio between them based on nucleosynthesis calculations. The observed ratio was significantly lower, not by a small margin, by enough to make the authors conclude that supernovae alone cannot account for the plutonium-244, which means something else is contributing, and the leading candidate for that something else is neutron star mergers, kilonovae, two dead stellar cores spiraling into each other at a significant fraction of the speed of light, and colliding in an event so violent that it makes a supernova look restrained. Neutron star mergers are now known to be prodigious factories of R-process elements. This was confirmed in 2017 when the gravitational wave event GW 170817 was followed by an optical counterpart that showed unmistakable signatures of R-process nucleosynthesis: gold, platinum, uranium, and, yes, plutonium. Wallner himself said it. Quote, "The story is complicated. Possibly this plutonium-244 was produced in supernova explosions, or it could be left over from a much older but even more spectacular event, such as a neutron star detonation." End quote. So what is sitting on the ocean floor is not just debris from a dead star. It is debris from the most violent processes the universe is capable of producing. The atoms in that Pharomeganin's crust were forged in conditions so extreme that atomic nuclei were being assembled by raw neutron bombardment, one neutron at a time, faster than the resulting nuclei could decay. And those atoms drifted through space for millions of years and landed on Earth and settled to the bottom of the Pacific Ocean and have been sitting there, radioactive, waiting for someone to find them. And you were never told. I want to come back to something I said earlier. I said the cosmic rays from the supernova at 2.5 million years ago were being reflected. They were being bounced back toward Earth by something. And I said that the thing doing the bouncing is what makes this story so much bigger than one dead star. This is the part where the scale of what is happening expands by several orders of magnitude. Because the reason the cosmic rays were trapped is that Earth is sitting inside a structure created by dead stars, a structure that surrounds our entire solar system right now. And you have been living inside it your whole life without knowing. It is called the local bubble. In January of 2022, a team led by Catherine Zucker published a paper in Nature that for the first time mapped this structure in 3 dimensions. Zucker, Goodman, Alves, Bialy, Foley, Spiegel, Groschedel, Finkbeiner, Burkert, Knie, and Swigum. Star formation near the Sun is driven by expansion of the local bubble. Nature, volume 601, pages 334 through 337. Catherine Zucker earned her doctorate at Harvard in 2020, working with Alyssa Goodman and Douglas Finkbeiner. She was a NASA Hubble Fellow at the Space Telescope Science Institute and is now a federal astrophysicist at the Smithsonian Astrophysical Observatory. She is in her early 30s, and the paper she published in Nature at the age of 28 is one of the most important pieces of galactic cartography produced in the past decade. Here is what she found. The Sun is sitting inside a roughly spherical cavity in the interstellar medium. This cavity is approximately 1,000 light-years across. Its current modeled radius is 165 parsecs, plus or minus 6 parsecs, which works out to about 540 light-years in every direction. Inside the cavity, the gas is extremely thin and extremely hot. The density is about 5,000ths of a particle per cubic centimeter, which is roughly 100 times less dense than the average interstellar medium. The temperature is around 1,000,000 degrees Kelvin. This cavity was not always here, it was created, carved out of the interstellar medium by a series of supernovae over the past 14 million years. How many supernovae? Zucker's team, using Gaia astrometry to trace the motions of young stars on the bubble's surface backward in time, and combining that with a momentum analysis of the expanding shell, estimated approximately 15, range 8 to 26, at 1 sigma. 15 dead stars detonating one after another over the course of millions of years in a region of space called the Scorpius-Centaurus-Ob association, specifically in 2 subclusters called Upper Centaurus Lupus and Lower Centaurus Crux. These are stellar nurseries where massive, short-lived stars form in clusters, burn through their fuel in 10 to 20 million years, and then explode, one after another, like a chain of bombs going off in slow motion over astronomical timescales. The first of these supernovae detonated approximately 14.4 million years ago, plus or minus about 700,000 years. At that time, the Upper Centaurus Lupus and Lower Centaurus Crux subclusters were about 15 parsecs apart and roughly 300 parsecs from where the Sun is now. The explosions began. Each one blew a little more of the interstellar medium outward. Each one heated the gas a little more. Each one expanded the cavity a little further. And the result, after 15 explosions over 14 million years, is the structure the Sun is sitting in right now. A 1,000 light-year wide bubble of hot, thin gas still expanding outward at 6.7 kilometers per second, having swept up an estimated 1.4 million solar masses of interstellar material and compressed it onto its surface. And here is the part that makes this personal. The Sun did not form inside the local bubble. The Sun is 4.6 billion years old. The bubble is 14 million years old. When the first supernova went off, the Sun was hundreds of parsecs away, orbiting the center of the galaxy on its own trajectory, minding its own business. The bubble was carved in a region of space the Sun had nothing to do with. But about 5 million years ago, the Sun's galactic orbit carried it into the bubble. João Alves, one of Zucker's co-authors, said it clearly. Quote, "When the first supernova that created the local bubble went off, our Sun was far away from the action. But about 5 million years ago, the Sun's path through the galaxy took it right into the bubble, and now the Sun sits, just by luck, almost right in the bubble's center." End quote. Just by luck, just by the random dynamics of galactic orbits, the Sun drifted into a cavity blasted open by dead stars, and now happens to be sitting near its center. And the iron 60 on the ocean floor and on the Moon, the 2 pulses at 2.5 and 7 million years ago, those correspond to supernovae that detonated while the Sun was inside the bubble, or just entering it. The debris did not have to cross hundreds of light years of dense interstellar medium. It was already in the same cavity. The delivery was local, and the walls of the bubble, the compressed shell of gas and dust on its outer surface, those walls are magnetized. They carry the magnetic signatures of the supernovae that created them. And when cosmic rays from a supernova inside the bubble hit those walls, they bounce back. They are reflected by the magnetic fields in the shell, back toward the interior, back toward Earth, again and again for 100,000 years. That is why the cosmic ray bombardment lasted so long. That is why the muon radiation persisted for roughly 100 millennia. The Earth was sitting inside a magnetic cage made of dead stars, and every time the cosmic rays tried to leave, the cage sent them back. I want to stop here and make sure the weight of this lands properly. You are living inside a cavity in the galaxy. That cavity was created by 15 stars that exploded over the past 14 million years. The sun drifted into it 5 million years ago. The walls of the cavity are still expanding. Every young star within 500 light years of Earth, every star formation region in the local neighborhood was born on the surface of this bubble, pushed into existence by the same explosions that carved the cavity. You are inside the aftermath. You have always been inside the aftermath. The night sky you see is shaped by dead stars. The region of space your solar system occupies was cleared for you by violence on a scale that is genuinely difficult to comprehend. And the debris from that violence is in our ocean. It is on our moon. And as of 2026, we know it is falling on Antarctica right now. But I have been holding a thread, and I need to pick it up now. I told you this was about the extinction of the largest predator that ever lived. I told you about the Plio-Pleistocene marine megafauna extinction. 55% of marine mammal genera gone. 43% of sea turtle genera gone. I gave you the numbers, but I have not given you the mechanism in full. And the mechanism is what makes this story something you will not be able to stop thinking about. Because Melott's model is not speculative. It is mechanistic. It follows the physics step by step. And at each step, the physics is well established and non-controversial. The controversy, if you can call it that, is not about whether these effects are real. It is about whether they are sufficient. And that is a very different kind of argument. Step 1. A core collapse supernova detonates at approximately 50 parsecs from Earth. This distance is consistent with the Iron 60 measurements, with the lunar data, and with the local bubble dynamics. The progenitor star had a mass of at least 8 solar masses. When its core collapsed, it released roughly 3 times 10 to the 46 joules of energy. Most of that energy went into neutrinos, which pass through everything and do essentially nothing. A small fraction, roughly 1%, went into the kinetic energy of the ejector, and an even smaller fraction, but still an enormous absolute number, went into accelerating cosmic rays in the expanding shock front. Step 2. The cosmic rays reach Earth. This happens not instantaneously, but over hundreds to thousands of years, depending on the magnetic field geometry between the supernova and the solar system. The protons arrive with energies ranging from hundreds of mega-electron volts to hundreds of giga-electron volts. When they hit the upper atmosphere, they initiate hadronic cascades. Each incoming proton generates a shower of secondary particles, pions, which decay into muons and neutrinos, neutrons, which scatter and cause further reactions, and electromagnetic cascades of electrons and photons. Step 3. The atmospheric chemistry changes. The cosmic ray protons and their secondary particles catalyze the formation of nitrogen oxides in the stratosphere, specifically nitric oxide and nitrogen dioxide. These nitrogen oxides are potent ozone destroyers. They enter the same catalytic cycles that chlorofluorocarbons do, but instead of being introduced at the surface and slowly migrating upward, they are produced directly in the stratosphere by the cosmic rays themselves. The result is ozone depletion of 15 to 40% depending on latitude, with the strongest effects at the poles where the magnetic field funnels charged particles downward. Step 4. With the ozone reduced, ultraviolet B radiation at the surface increases by roughly 50% globally, with higher increases at higher latitudes. UVB in the 280 to 315 nanometer range is biologically active. It damages DNA directly. It suppresses immune function in mammals. It causes cataracts. It inhibits photosynthesis in phytoplankton, the base of the marine food web. A sustained 50% increase in UVB would stress every photosynthetic organism in the surface ocean and every animal that depends on them. Step 5. And this is where it gets truly dark. The muon flux at the surface increases by a factor of roughly 150. Muons are produced when cosmic ray protons generate pions in the upper atmosphere, and those pions decay into muons. A muon has a mean lifetime of about 2.2 microseconds. But because the muons are created at relativistic speeds, time dilation extends their effective lifetime enough that many of them reach the surface before decaying. And unlike UVB, which is stopped by a few meters of water, muons penetrate. They penetrate rock. They penetrate water to depths approaching 1 kilometre. They penetrate you. Right now, the background muon flux at sea level is about 10,000 muons per square meter per minute. A 150-fold increase means 1.5 million muons per square meter per minute. And the radiation dose from those muons is not trivial. Melott's 2018 astrobiology paper, working with Marino and Paolucci, calculated the absorbed dose at various ocean depths. At depths of a few hundred meters, the muon radiation dose from the supernova exceeded the total present-day surface radiation from all natural sources combined. For organisms living in the mesopelagic zone, between 200 and 1,000 meters, the radiation field they were swimming through would have been many times what any organism on Earth's surface experiences today. And here is the kicker. Radiation damage scales with body mass. A larger body has more cells. More cells means more targets. More targets means more mutations. More DNA damage per unit time. More cancer. More reproductive failure. Which means the kill selectivity of supernova muon radiation is exactly what you see in the fossil record. It preferentially targets the large, the megafauna, the animals like Megalodon, which, even if it went extinct somewhat before the peak of the supernova bombardment, lived through the leading edge of a cosmic ray surge that had been building for hundreds of thousands of years before the Iron 60 pulse peaked. The animals like the giant sea turtles, the oversized cetaceans, the enormous filter feeders, and apex predators that defined Pliocene ocean ecology. I should be clear about something. Melott never claimed that the supernova was the sole cause of the Plio-Pleistocene marine megafauna extinction. He is too careful a scientist for that. The extinction likely had multiple drivers, including the closure of the Central American Seaway, changing ocean circulation patterns, and the broader cooling trend that was transforming Earth's climate. What Melott argued is that the supernova bombardment added a radiation stressor on top of all of these other pressures, a stressor that specifically targeted the largest marine organisms at exactly the time those organisms were already under ecological stress. He published through a University of Kansas press release where he contextualized the scale of Megalodon for a general audience. The framing he used has stuck with me. He talked about the great white shark from the movie Jaws and pointed out that the animal in the film was enormous, and that was merely a great white. Megalodon was the length of a school bus, and it disappeared during a period when the skies above its ocean were filled with radiation from a dead star. Think about that image. A 60-foot shark hunting in an ocean that is being quietly irradiated from above by cosmic debris from a stellar explosion that happened before anything remotely human walked the Earth. The shark does not know. It cannot know. It swims and feeds and breeds, and slowly, over thousands of generations, the population declines. Reproductive rates drop. Juvenile survival falls. The species shrinks and disappears, and the cause is invisible. It is not a predator. It is not starvation. It is radiation from a star that died 100 light-years away, reflected by the magnetic walls of a cavity blown open by 14 other dead stars over the previous 12 million years. That is the reality of where you live. And I am not done, because the radiation did not just kill things. It may have also made things. And this is the part of the story that was published in January of 2025, and that, once again, nobody talked about. Nojiri, Globus, and Ramirez Ruiz, working out of UC Santa Cruz, published a paper in the astrophysical journal Letters in January 2025, volume 979, article L18. The title is Life in the Bubble: How a Nearby Supernova Left Ephemeral Footprints on the Cosmic Ray Spectrum and Indelible Imprints on Life. It is one of the most remarkable titles I have read in a scientific paper in years, and the content matches the ambition. What they did is model the cosmic ray spectrum enhancement from the 2.5 million year supernova event, taking into account the confinement effect of the local bubble's magnetic walls. And then they looked for biological events that correlated with the timing of the cosmic ray surge. And they found 1. In Lake Tanganyika, the deepest lake in Africa and the second deepest in the world, there is a documented burst of viral speciation in fish populations between 2 and 3 million years ago. A sudden increase in the diversity of viruses infecting cichlid fish. The timing aligns with the supernova-derived cosmic ray surge. Nigerian colleagues argue that the elevated radiation, specifically the muon component that penetrates water to significant depths, could have increased the mutation rate in viral genomes enough to drive a speciation event. Let me say that again more slowly because I want to make sure it registers. A star exploded 100 or so light years away. Its cosmic rays reached Earth. Those cosmic rays were trapped by the local bubble's walls, bouncing back and forth for 100,000 years. The muons from those cosmic rays penetrated deep into the largest lakes in Africa, and the radiation may have accelerated the evolution of viruses inside those lakes. A dead star may have shaped the viral ecology of fish in a lake in East Africa. The universe is not a passive backdrop. It is an active participant in the story of life on this planet, and the mechanisms by which it participates are not gentle. They are violent. They are radioactive. They involve the deaths of stars, the destruction of ozone, the bombardment of muons, and the reshaping of genomes. And they are happening right now. I need to address the title of this story, because if you clicked on this video, you likely did so because of a claim about the dinosaurs. And the relationship between supernovae and the dinosaur extinction is something I need to handle carefully, because it is a real scientific question with a complicated answer. The Cretaceous Paleogene extinction event, the one that killed the non-avian dinosaurs 66 million years ago, is dominated by one thing: the Chicxulub impact. An asteroid roughly 10 to 15 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico and released energy equivalent to roughly 10 billion Hiroshima bombs. The evidence is overwhelming. The iridium anomaly at the KPG boundary, a thin layer of iridium found in geological strata worldwide, is the fingerprint of that impact. Iridium is rare on Earth's surface, but common in asteroids. The crater itself, approximately 180 kilometers wide, has been found and dated. The story of the dinosaur extinction is fundamentally an impact story. But there is a question that sits alongside it. A question that the Iron 60 record cannot directly answer, but that researchers at the Australian National University have flagged as worthy of investigation. Could a supernova have also played a role, not as the primary driver, but as a contributing stressor, an environmental insult that weakened ecosystems before the asteroid arrived? Here is the problem with answering that question. Iron 60 has a half-life of 2.62 million years. 66 million years is roughly 25 half-lives. Any Iron 60 that was deposited at the KPG boundary has long since decayed. The geological clock for that isotope only extends back about 15 million years. You cannot use Iron 60 to look for supernovae in the late Cretaceous. The signal is gone. Wallner's team at ANU has flagged an exploratory project to look for other potential supernova signatures in KPG boundary samples, using longer-lived isotopes or indirect markers. As of the most recent information available, no positive result has been published. The search is open. The evidence is absent. The idea is speculative. What I can tell you is this: the galaxy does not stop exploding just because we cannot detect the debris 66 million years later. The Milky Way produces roughly 2 to 3 supernovae per century. That estimate comes from Tammann, Loeffler, and Schroeder, 1994, published in the Astrophysical Journal Supplement Series, Volume 92, page 487. About 85% of those are core collapse supernovae from massive progenitors. Over 66 million years, that is hundreds of millions of supernovae in the galaxy. The question is not whether any of them were close to Earth during the late Cretaceous. The question is how close, and whether the timing aligned with any of the stresses that were already accumulating before Chicxulub hit. There is a broader pattern here. Nersheviv and others have argued that there is a correlation between the solar system's passage through the Milky Way's spiral arms, where the density of massive stars and therefore the supernova rate is higher, and the timing of major glaciation episodes on Earth. The argument involves cosmic ray modulation of cloud formation via the Svensmark hypothesis, which proposes that cosmic ray ionization in the lower atmosphere creates cloud condensation nuclei, increasing cloud cover and cooling the planet. This hypothesis remains contested. The cloud experiment at CERN has shown that cosmic ray ionization does produce aerosol particles, but the magnitude of the effect and whether it is sufficient to drive global climate change is unresolved. What is not contested is the basic physics. Cosmic rays do ionize the atmosphere. Ionization does affect atmospheric chemistry. Supernovae do produce cosmic rays, and the Earth has been passing through regions of elevated supernova activity for its entire history. The question is one of magnitude, not mechanism. And the magnitude for the event 2.5 million years ago is not trivial. Melott and Thomas published a paper in 2019, archived on arXiv as 1810.01995, that examined whether supernova-driven cosmic rays could have contributed to the onset of the Pleistocene ice ages through atmospheric ionization and subsequent climate effects. Their estimate was that the nitrogen flux enhancement at 50 parsecs was approximately 10% above background. Their conclusion was that this was, quote, probably too small for dramatic changes, end quote. But they also noted that the sustained duration of the cosmic ray bombardment, 100,000 years, meant that even a modest effect could accumulate. I want to be honest about the state of this science because the audience deserves honesty, not dramatic oversimplification. The connection between the 2.5 million year supernova and the onset of the Pleistocene ice ages is plausible but unproven. The connection between the supernova Muon flux and the marine megafauna extinction is stronger but still not definitive. The connection between the supernova cosmic ray surge and the virus speciation event in Lake Tanganyika is provocative but preliminary. And in late 2026, a paper by Ofer and colleagues in Nature Astronomy examined cosmogenic nuclide profiles, specifically beryllium-10 and aluminum-26, in deep ocean samples, and found that those profiles do not show the strong cosmic ray increase at 2 to 3 million years ago that the simple one supernova model predicts. This complicates the picture. It does not destroy it. The OPA result could mean the cosmic ray flux was weaker than modeled, or briefer, or that the cosmogenic nuclide production rate models need refinement. But it is a genuine scientific descent, and I would be lying to you if I pretended it did not exist. This is what real science looks like. Not a clean story with a neat conclusion. A messy, ongoing argument where the data points in several directions simultaneously, and the people doing the work disagree about how to interpret it. The iron-60 is real. The plutonium-244 is real. The local bubble is real. The marine megafauna extinction is real. The correlations in timing are real. What remains genuinely uncertain is the causal chain that connects them. And anyone who tells you they have the definitive answer to that causal question is selling you something. What I can tell you, what is not uncertain, what has been confirmed by multiple independent teams across 3 decades of measurement, is this. Stars have exploded near Earth within the recent geological past. Their radioactive debris is in our ocean floor, on our moon, and in Antarctic ice. The debris from at least one of those explosions correlates in time with one of the largest marine extinction events since the end of the Cretaceous. Earth sits inside a cavity blown open by 15 or more of these explosions over the past 14 million years, and the debris is still arriving. And that last part, the still arriving part, is where I need to take you now. Because in 2026, a paper was published in Physical Review Letters by Dominic Cole and colleagues at the Helmholtz Center Dresden-Rossendorf and the Australian National University that changed the timeline of this story. Not backward into deep time, forward. Into the present, Cole had been working on this problem for years. In 2019, he and Wallner published a detection of iron-60 in modern Antarctic snow. Snow that had fallen within the past 20 years. That result, published in Physical Review Letters, showed that iron-60 was not just an ancient signal locked in ocean crusts millions of years old. It was current. It was actively being deposited. The Earth was picking up supernova debris in real time. But the snow result raised a question. Was the iron-60 in the snow from the same source as the iron-60 in the ocean crust? Was it the tail end of the 2.5 million year event, the last whisper of a supernova that had been raining debris for over 1 million years? Or was it from something else? Cole's 2026 paper went after this question by looking at a deeper archive. Ice cores from the EPICA EDML drilling project at Conan Station, Antarctica. These cores had been drilled in the early 2000s and provided a continuous record of snowfall going back over 800,000 years. Cole's team analyzed sections spanning from 40,000 to 81,000 years before present, and they found iron-60. But the signal intensity was different from the modern snow. It was about 5 times lower. That is an enormously important number. If the iron-60 were coming from a single ancient source that was gradually fading over time, you would expect the signal to decrease monotonically as you look back in time. Younger snow would have more, older ice would have less, because the source, whatever it is, would be getting farther away or running out of debris to deliver. But that is not what Cole found. The modern snow had more iron 60 than the 40,000 to 81,000-year-old ice. The signal went up, not down, as you approach the present. That pattern is inconsistent with a smoothly fading ancient source. It is consistent with something else entirely. It is consistent with Earth entering a new patch of interstellar dust in the relatively recent past, not millions of years ago, thousands of years ago. And that patch has a name. It is called the Local Interstellar Cloud, sometimes abbreviated LIC. It is a small, warm cloud of partially ionized gas, roughly 30 light-years across, that the Sun has been passing through for the past few tens of thousands of years. We know the Sun is inside it because the Ulysses and Ibex spacecraft have directly detected interstellar neutral atoms, primarily helium, flowing into the solar system from the direction consistent with the Sun's motion through the cloud. The local interstellar cloud is itself a piece of the local bubble's interior. It is one of several small cloudlets floating inside the larger cavity, and it appears to contain iron 60, not from the 2.5 million year supernova directly, but from the integrated accumulation of supernova debris that has been deposited inside the bubble over millions of years. The bubble is not empty. It is a cavity, yes, less dense than the surrounding interstellar medium by a factor of 100, but it is not a vacuum. It contains filaments and cloudlets of gas and dust, and those filaments carry the chemical signatures of every supernova that ever detonated inside it. And the Sun is flying through one of those filaments right now. I need you to visualize this, because the scale is important, and I do not think most people have any intuition for it. The Sun is moving through the galaxy at roughly 230 kilometers per second, relative to the galactic center. Relative to the local interstellar cloud, it is moving at roughly 26 kilometers per second. That is 94,000 kilometers per hour. Every hour, the Sun and every planet in its system moves through 94,000 new kilometers of interstellar space. And the interstellar space we are moving through right now contains radioactive debris from dead stars. The Iron 60 landing on Antarctica is not ancient debris still settling from a supernova that happened 2.5 million years ago. It is fresh pickup. The Earth, the Moon, the entire solar system is plowing through a cloud of stardust, like a car driving through a snowstorm, and the snow is radioactive. Now I want to go back to the beginning of this story and pick up a thread I introduced and then set aside. I said that the first evidence was published in 1999. That is 27 years ago. I said that Wallner's global confirmation was published in 2016. That is 10 years ago. I said that the plutonium was published in 2021. That is 5 years ago. I said that the local bubble mapping was published in 2022. That is 4 years ago. And I said that the Antarctic ice core result was published in 2026. That is this year. This is not an obscure corner of science. These papers appeared in the most prestigious journals on the planet: Nature, Science, Physical Review Letters, the Astrophysical Journal. The authors work at major research institutions: ANU, Harvard, the Smithsonian, the Technical University of Munich, the Helmholtz Center, UC Santa Cruz, the University of Kansas. The work is funded by national science agencies. The results are replicated across multiple independent labs, and almost nobody knows about it. I have talked to people with graduate degrees in physics who are unaware that iron 60 had been found on the ocean floor. I have talked to science educators who did not know about the local bubble. I have encountered people who follow space news closely, who can tell you the names of every Mars rover, who are completely unfamiliar with the Wallner papers. This is not a failure of the scientists. They published. They gave press releases. Wallner did interviews. Zucker's team released a spectacular three-dimensional animation of the local bubble that was featured in media outlets around the world when it came out. Melott published through the University of Kansas press office. The information is out there. The failure is in the way science communication is structured. These results do not fit into a single neat category. They are not astronomy in the way people think of astronomy, which is telescopes and pretty pictures of nebulae. They are not paleontology, which is fossils and dinosaur bones. They are not nuclear physics, which is reactors and particle accelerators. They are all of these things at once. And our institutions, our media, our educational systems are organized by category. There is no desk at a news organization labeled "What Dead Stars Did to Ocean Life." There is no beat reporter covering this. There is no documentary series. There is no chapter in any textbook I have found that connects the iron 60 in the ocean crust to the local bubble, to the marine megafauna extinction, to the plutonium that should not exist. And so the story sits in the primary literature, fragmented across a dozen subdisciplines known to a few hundred specialists, and invisible to the public. That should make you angry, not at any individual, but at the structure, at the system that produced this silence. Because the silence is not neutral. The silence means that the picture of where you live, the picture you probably carry around in your head, is incomplete in a way that matters. You think of Earth as a static platform, a stable stage on which life performs. The ground is solid, the sky is blue, the stars are far away and pretty and inert. This picture is wrong. The ground is bombarded. The sky is a shield that has been compromised before and will be again. The stars are not inert. Some of them are dead, and the dead ones are still reaching across light years to touch you. The atoms in your bones include elements forged in supernovae. This is a fact you probably already knew. The popular version, the Carl Sagan version, is "We are star stuff." And that is true. But the implication that usually follows, the warm, reassuring implication that we are connected to the cosmos in a beautiful and poetic way, obscures a darker truth. The cosmos is connected to us in a way that is not always beautiful. Sometimes it is destructive. Sometimes it kills. Sometimes it reaches across space and time and changes the trajectory of life on an entire planet. And the evidence that it has done so is sitting in the geological record, confirmed, published, replicated, and largely unknown. I want to tell you about the people in this story one more time, because the people matter as much as the physics. Klaus Knie counted 7 atoms of iron, 60 in 1999, and opened this entire field. He is now at the GSI Helmholtz Center for Heavy Iron Research in Darmstadt, working on the high-intensity proton LINAC and antiproton target for the FAIR project, which is one of the largest accelerator facilities in the world. He moved on from iron 60, but the work he started never stopped. Gunther Korscheneck was Knie's mentor at the Meyer-Leibniz laboratory in Munich. He spent decades building the accelerator mass spectrometry program that made the detections possible. He is the person who took the lunar samples and ran them through the tandem accelerator and confirmed that the moon carries the same signal as the ocean floor. His career was a slow, patient accumulation of capability that culminated in a result that rewrites where we fit in the galaxy. Anton Wallner took what Knie started and made it global. He gathered samples from 3 oceans and the Moon and the Antarctic snow and built the most comprehensive map of supernova debris deposition on Earth that exists. He found the plutonium. He co-led the Antarctic icework. He moved from ANU to the Helmholtz Center in Dresden, and the program he built is the reason we know that this is not over, that the debris is still falling, that the story is current. Adrian Melott, the cosmologist turned astrobiphysicist at the University of Kansas, asked the question nobody else wanted to ask. What did it do to life? He built the models, he calculated the muon doses, he wrote the papers connecting the isotope data to the extinction record. And he did this knowing that the connection is contested, knowing that the causal chain is not proven beyond doubt, knowing that some colleagues consider the whole line of inquiry premature. He did it because the data demanded the question be asked, even if the answer is not yet certain. Catherine Zucker mapped the cavity we live in. She was 28 when the paper came out. She used Gaia astrometry and 3-dimensional dust mapping and the GLUE data visualization software developed by her advisor Alyssa Goodman, and she produced a result that placed the sun's current location in a galactic context that had never been visualized before. Before Zucker's paper, the local bubble was a vague concept. After her paper, it was a measured structure with a known radius, a known expansion speed, a known age, and a known origin. Dominic Cole found iron 60 in ice that is younger than agriculture. He found it in snow that is younger than the pyramids. He showed that the story of supernovae and Earth is not something that happened millions of years ago and stopped. It is happening now. The debris is landing on this planet while you listen to this. These are the people who built this story. And the fact that their names are not widely known, that this narrative has not penetrated public consciousness, is a failure of communication so profound that it borders on the scandalous. Because the implications of their work, taken together, change the picture of where we live in a way that I think most people are not prepared for. Here is the picture. Earth does not orbit the sun in a generic patch of galactic space. It orbits the sun inside a specific structure, a cavity blown open by the deaths of 15 massive stars over 14 million years. That cavity is approximately 1,000 light years across. Its walls are magnetized. Its interior is hot and thin. The sun entered this cavity 5 million years ago by the random chance of its galactic orbit. The cavity is still expanding. The walls are still moving outward at 6.7 kilometers per second. Inside the cavity, remnants of the explosions that created it still linger. Filaments and cloudlets of gas and dust carrying radioactive isotopes. The sun is currently passing through one of these cloudlets, the local interstellar cloud, which contains iron 60 from past supernova events. The iron 60 is being swept up by the solar system and deposited on Earth and the Moon as we move through the cloud. 2 of the supernovae that contributed to the cavity detonated close enough to Earth within a few hundred light years to deposit measurable amounts of iron 60 on the ocean floor. The younger of these events, approximately 2.5 million years ago, is temporally correlated with one of the largest marine extinction events since the end of the Cretaceous. The cosmic ray flux from this event, trapped and reflected by the cavity walls, bombarded Earth with muon radiation at levels sufficient to irradiate the ocean to depths of nearly a kilometre for roughly 100,000 years. Alongside the iron 60, plutonium-244 from the same general time period has been found on the ocean floor. This plutonium was created by the rapid neutron capture process in events so violent They defy intuition. Supernovae, possibly neutron star mergers, possibly both. The ratio of plutonium to iron in the samples suggests that supernovae alone cannot account for all the heavy elements being delivered to Earth. Something even more extreme contributed, and this is not over. I keep saying that because it bears repeating. This is not a story about the past. It is a story about the present. The Iron 60 in Antarctic snow fell in your lifetime. The solar system is moving through the local interstellar cloud right now at 94,000 kilometers per hour. And the cloud contains the chemical legacy of dead stars. The local bubble's walls are still expanding, still carrying the magnetic memory of 15 detonations. The Scorpius-Centaurus Association still contains massive stars, some of which will go supernova in the next few million years. And the question of when the next nearby supernova will occur is not a question with a comfortable answer. The nearest red supergiant star that is commonly cited as a supernova candidate is Betelgeuse. It is the bright reddish star in the constellation Orion, the one on Orion's left shoulder. Betelgeuse is roughly 640 to 700 light-years away, depending on which measurement you use. Its mass is estimated at 11 to 20 solar masses. It is a dying star. It has exhausted the hydrogen in its core and is fusing heavier elements, bloating to a diameter of roughly 860 million miles. If you placed Betelgeuse where the Sun is, its surface would extend past the orbit of Jupiter. When Betelgeuse goes supernova, and it will go supernova, the question is when it will briefly become one of the brightest objects in the sky. Estimates suggest it could rival the full moon in apparent brightness for weeks or months. It would be visible during the day. It would cast shadows at night. It would be the most spectacular astronomical event witnessed by modern civilization. And it would do absolutely nothing to Earth. 640 light-years is roughly 200 parsecs. That is 4 times farther than the danger threshold calculated by Melott and Thomas. At that distance, the cosmic ray flux would be negligible. The Iron 60 deposition would be undetectable. The ozone effect would be zero. Betelgeuse is a spectacle, not a threat. Antares, the red supergiant in Scorpius, is similarly safe at roughly 550 light-years. It will also explode eventually. It will also be beautiful. And it will also be irrelevant to Earth's biosphere. The nearest known Type Ia supernova candidate is Ik Pegasi b, a white dwarf in a binary system roughly 150 light-years away, about 46 parsecs. That is within the Melott danger zone. But Ik Pegasi b is estimated to be at least 1 billion years from detonation, if it ever detonates at all. And by then, the proper motion of the system will have carried it far from its current location. So the immediate neighborhood is, by recent geological standards, quiet. There is no star within 30 parsecs that is poised to explode in the next 1 million years. The current solar system neighborhood is safe, for now. But that is a statement about the next 1 million years, not the next 10 million or the next 100 million. And the Iron 60 record tells us that over the timescales that matter for the evolution of life, nearby supernovae are not rare. They are routine. 2 confirmed events in the past 10 million years, 15 supernovae carving the local bubble over 14 million years, a galactic supernova rate of 2 to 3 per century. The galaxy is a violent place. We happen to be living in a quiet moment. And I use the word moment deliberately, because in galactic terms, that is exactly what it is. A moment, a pause between storms. I want to go deeper into what the local bubble actually means for us, because I think the physical reality of it has not been fully absorbed even by people who know the name. When Catherine Zucker mapped the bubble in 3 dimensions, she did not just find a cavity, she found a machine. An active, dynamic, still-running machine that is reshaping the galaxy around us in real time. Every major molecular cloud complex within 500 light-years of Earth sits on the surface of the bubble. Taurus, Ophiuchus, Lupus, Chameleon, Corona Australis, Musca, Pipe Nebula, all of them. These are the regions where new stars are forming right now, where gas and dust are collapsing under gravity to ignite new nuclear fires. And all of them were swept up by the expanding shock wave of the bubble and compressed onto its surface. What this means is extraordinary. Every young star within 500 light-years of Earth was born because of the supernovae that created the bubble. The explosions did not just destroy, they created. They compressed gas. They triggered collapse. They ignited new generations of stars. Some of those new stars are massive enough that they will themselves go supernova in the next 10 to 20 million years. And when they do, they will carve new cavities, create new bubbles, and trigger new generations of star formation. The galaxy is a system of nested explosions. Supernovae create the conditions for new stars, which become new supernovae, which create conditions for more new stars. The process is self-sustaining, self-organizing, and violent. And we are inside it, not watching from a distance, inside it. The sun is literally inside the blast radius of the most recent round of detonations, bathing in their debris, surrounded by the stars they created, and moving through the radioactive remnants of their ejecta. You were taught, or at least you absorbed the impression, that the solar system exists in a kind of benign vacuum, that space is empty and cold and far away, that the nearest star is Alpha Centauri, 4.3 light-years distant, and that nothing between here and there matters. That impression is wrong. The space between here and Alpha Centauri is not empty. It is structured. It is shaped by violence. It carries the chemical and radioactive memory of every star that has died in this neighborhood for the past 14 million years. And the sun is not merely drifting through it. The sun is interacting with it, sweeping up its dust, collecting its atoms, depositing them on the surfaces of its planets and moons. The Iron 60 on the Moon was not delivered by some exotic mechanism. It was delivered by the ordinary motion of the solar system, through space. The solar wind, the stream of charged particles that flows outward from the sun, creates a bubble of its own called the heliosphere. The heliosphere is roughly 120 astronomical units in radius, roughly twice the distance from the sun to Pluto. It is the sun's sphere of influence, the region where the solar wind dominates over the interstellar medium. At the edge of the heliosphere, the heliopause, the solar wind meets the interstellar medium and the two reach a rough equilibrium. But the heliosphere is not impenetrable. Neutral atoms from the interstellar medium can cross the heliopause because they carry no charge and are therefore unaffected by the solar wind's magnetic field. These neutral atoms, including neutral ion atoms, stream into the inner solar system and are ionized by solar UV radiation or charge exchange with the solar wind protons. Once ionized, they are picked up by the solar wind's magnetic field and can be deposited on any surface in the inner solar system. The Moon, Mars, Earth. This is the mechanism by which the Iron 60 arrived. It drifted as neutral atoms through interstellar space, crossed the heliopause, entered the inner solar system, was ionized by solar radiation, and settled onto the surfaces of planets and moons. Some of it sank through Earth's atmosphere and landed on the ocean. Some of it landed on ice sheets. Some of it was incorporated into the slow-growing ferromanganese crusts on the deep ocean floor. And some of it fell on the Moon, where it has been sitting undisturbed in the regolith for millions of years. The delivery mechanism is elegant and mundane at the same time. There is no dramatic event, no flash of light, no shockwave, just a slow, invisible rain of atoms from a dead star drifting through space, crossing the boundary of the solar system, and settling onto whatever surface they encounter. And the fact that we can detect individual atoms of this rain, that we can count them one by one in an accelerator and determine which geological layer they belong to, and therefore, when they arrived, is one of the most remarkable achievements in experimental physics of the past 3 decades. And it is only the beginning, because the same accelerator mass spectrometry techniques that detected iron-60 and plutonium-244 are now being applied to other isotopes: manganese-53, iodine-129, hafnium-182, curium-247. Each of these isotopes has a different half-life and a different production pathway. Some are made in supernovae, some in neutron star mergers, some in both. By measuring multiple isotopes in the same geological samples, researchers can begin to disentangle the contributions of different astrophysical events. They can determine not just that a supernova happened, but what kind of supernova it was, how massive the progenitor star was, whether the R process occurred in the supernova itself or in a separate event like a neutron star merger. And eventually, perhaps, they can build a complete history of the astrophysical events that have affected the inner solar system over the past 10 to 15 million years. Wallner's group is leading this effort. The Helmholtz Center in Dresden has one of the most sensitive AMS facilities in the world, and the program Wallner has built there is systematically working through the periodic table of interstellar traces. Each new isotope detection is another data point in what amounts to a geological record of the galaxy's behavior in our neighborhood. And the geological record is telling a story that is more complicated and more interesting than anyone expected. Consider the plutonium. The fact that plutonium-244 shows up in the same time windows as iron-60, but in a ratio that does not match supernova models, means that the interstellar medium around us carries the legacy of more than just supernovae. Neutron star mergers, events that occur perhaps once every 10,000 to 100,000 years in the Milky Way, produce enormous quantities of R process elements and distribute them over scales of hundreds of light years. The plutonium in the ocean crust may be the residue of a neutron star merger that occurred millions of years before the supernovae that deposited the iron-60, a merger that seeded the local interstellar medium with heavy R process elements, which were then swept up and redeposited by the supernova shockwaves. If that is the case, the atoms on the ocean floor carry the integrated memory of multiple violent astrophysical events spanning millions of years. Not one supernova, not one merger. A sequence, a history, written in atoms on the floor of the Pacific Ocean, readable by anyone with a tandem accelerator and the patience to count 1 atom per hour for weeks on end. There is something almost sacred about that. The ocean floor is a library, each ferromanganese crust a volume, each layer a page, each atom a letter in a story written by the galaxy. And the story is not about distant cosmic events that have nothing to do with us. The story is about what the galaxy has been doing to this planet for the past 14 million years, what it is doing right now, and what it will do next. I want to return to the question of what comes next, because I think there is a temptation when dealing with astronomical timescales to treat everything as safely remote. 1 million years from now, 10 million years from now. These numbers sound so large that they feel like never. They feel like they do not apply to us. They feel like someone else's problem. But consider this. The sun entered the local bubble approximately 5 million years ago. The genus Homo appeared approximately 2 to 3 million years ago. Anatomically modern humans appeared roughly 300,000 years ago. Civilization, in the sense of agriculture and permanent settlements, appeared roughly 12,000 years ago. Recorded history spans about 5,000 years. The Iron 60 peak at 2.5 million years ago, the one that correlates with the marine megafauna extinction, occurred at a time when our direct ancestors were walking the African savannas. Not modern humans, not even Homo erectus, but hominins, members of the genus Australopithecus or early Homo, creatures whose brains were evolving rapidly, whose bodies were adapting to a landscape that was drying out and opening up. And the landscape was drying out, in part, because of the climate shift at the Plio-Pleistocene boundary, the same boundary that correlates with the supernova signal, the same boundary that marks the onset of major northern hemisphere glaciation, the same boundary where a third of marine megafauna vanished. I am not claiming that a supernova made us human. That would be a wild overstatement of the evidence. But I am pointing out that the environmental pressures that shaped human evolution, the drying of Africa, the spread of grasslands, the cooling of the climate, these pressures coincided in time with a nearby stellar explosion whose effects on Earth's atmosphere, radiation environment, and climate are documented in the geological record. The coincidence may be just that, a coincidence. Or it may be that the galaxy, in destroying and creating, in killing and reshaping, in blasting cavities and compressing gas and raining debris, played some role in the cascade of events that eventually led to a primate that could build an accelerator and count the atoms. That thought is either deeply beautiful or deeply disturbing, depending on your temperament. I find it both. Let me bring this home. You live on a planet that is sitting inside a cavity blown open by 15 dead stars. The walls of that cavity are still expanding. They carry the magnetic memory of every explosion. Inside the cavity, filaments of radioactive debris drift through the thin, hot gas, and the sun is currently plowing through one of those filaments at 94,000 kilometers per hour. Every year, atoms of iron 60 that were forged in the core of a star that died before the first hominins walked upright settle onto the ice at the bottom of the world. 2.5 million years ago, one of those stars died close enough that its cosmic rays, reflected by the bubble's walls, bombarded Earth with muon radiation for 100,000 years. A third of large marine animal genera vanished. The climate shifted. Africa dried out, and somewhere on those new savannas, a lineage of primates began the long walk toward building the machines that would, 25 million centuries later, detect the debris of the star that may have helped create the conditions for their existence. The ocean floor is not just a record of Earth. It is a record of what the galaxy did to Earth. It is a transcript of stellar violence, written in atoms that should not exist here, deposited by processes so vast in scale that they take millions of years to complete, and preserved in layers of mineral that grow at 2 millimeters per million years. And the transcript is not finished. It is being written right now as you listen to this, one atom at a time, falling silently from space onto rock and ice and water. The people who wrote the papers that uncovered this story, Knie and Korschenek and Wallner and Melott and Zucker and Kohl, they did something that I think deserves to be recognized for what it is. They reached into the geological record and pulled out individual atoms, atoms that crossed interstellar space and drifted down through the atmosphere and settled into the deep ocean. And they counted those atoms one by one, over weeks and months of accelerator time. And they used those counts to reconstruct events that happened millions of years ago in a part of the galaxy hundreds of light years away. That is not just good science. That is an act of almost unreasonable ambition. To find individual atoms of a dead star on the floor of a living ocean and to use them to tell the story of what the galaxy has been doing to us. And the story they tell is not the reassuring one. The story is not that we are floating serenely through a benign void, insulated from the galaxy by distance and time. The story is that we are inside the blast zone. We have always been inside the blast zone, at least for the past 5 million years. The galaxy is not a backdrop. It is not a setting. It is an active participant in the story of life on this planet. It sends its debris. It irradiates our oceans. It strips our ozone. It shapes our climate. It may have contributed to the extinction of the largest marine predator that ever lived, and it is doing it right now, quietly, invisibly, one atom at a time, falling on Antarctic ice. Wallner said it in an early interview about the 2016 results. He called it an interesting coincidence that the supernova signals corresponded with the Plio-Pleistocene transition. He used the word coincidence, but there was something in the way he said it, the way he paused before the word, the way he qualified it with interesting. He knew it was not a coincidence, or at the very least, he knew that calling it a coincidence was the only safe thing to say, because saying what the data actually suggests, that a dead star contributed to reshaping the trajectory of life on Earth, including possibly our own lineage, is the kind of claim that a scientist cannot make without decades of additional evidence. And so he said, interesting coincidence. And the world moved on. The data did not move on. The iron 60 is still there. The plutonium is still there. The extinction is still there. The timing is still there. And now the Antarctic ice is there too, extending the story from the deep past into the measurable present. And every year, Wallner's group and Cole's group and the teams at ANU and Munich and Dresden add more isotopes, more samples, more data points to a picture that keeps getting more detailed and more uncomfortable. The iron 60 has a half-life of 2.62 million years. In another 2.5 million years, half of the iron 60 currently sitting in the ocean crust will have decayed. The geological record of the most recent supernova will be fading, but there will be new records. New supernovae will occur, new debris will fall, new layers of ocean crust will capture new atoms. And if there is anyone here in 2.5 million years to build accelerators and count atoms, they will find the fingerprints of events we have not yet seen. The galaxy does not stop. There is one more detail I want to leave you with. In 2020, Wallner published a paper in the Proceedings of the National Academy of Sciences based on 5 deep-sea sediment samples covering the last 33,000 years. He found iron 60 deposition that was roughly continuous over that entire period. Not a spike, not a pulse, a steady, ongoing rain. The iron 60 has been falling for at least 33,000 years, through the last ice age, through the development of agriculture, through the rise and fall of every civilization that has ever existed. Every empire, every revolution, every scientific breakthrough, every war, every cathedral, every love letter ever written, happened on a planet that was being quietly dusted with the radioactive remains of a dead star. And nobody knew, not because the information was hidden, but because nobody had built the machine to see it yet. Knie built the machine. He pointed it at a rock from the bottom of the ocean, and he found 7 atoms. 7 atoms. That is where this started. And from those 7 atoms came a story that rewrites our understanding of where we live and what the galaxy has been doing to us. A story of dead stars and radioactive rain and a bubble carved by violence. A story of 60-foot sharks irradiated by muons from a stellar corpse. A story of plutonium that traveled from a dying neutron star through interstellar space to the floor of the Pacific Ocean. A story of a cavity 1,000 light years wide that the sun wandered into by accident 5 million years ago, and that we are still inside. And the story is not over. The debris is still falling. The bubble is still expanding. The galaxy is still working. Somewhere out there, in the Scorpius-Centaurus Association, or somewhere else in the spiral arm, massive stars are burning through their fuel, approaching the end of their nuclear lives, getting ready to add their own iron 60 to the interstellar medium. And a few million years from now, some of that iron will drift through space and cross the heliopause and settle onto whatever surface is waiting. If there is still an ocean, it will land on the ocean floor. If there is still ice, it will land on the ice. If there is someone here to find it, they will count it one atom at a time and add another page to the transcript. The ocean floor remembers what the sky did, and the sky is not finished. But I realize I have moved too quickly through some of this, and there are parts of this story that deserve more time. So let me go back. Let me go deeper into the parts that I think the numbers alone cannot convey. I want to talk about what a ferromanganese crust actually is, because the phrase rolls off the tongue easily enough, and it sounds like a technical abstraction. But the reality of the thing is stranger and more beautiful than the name suggests. A ferromanganese crust is a layer of minerals that precipitates directly out of seawater onto the surfaces of rocks on the ocean floor. It is made primarily of iron and manganese oxides, hence the name, and it forms at depths of between 400 and 7,000 meters, the deepest, coldest, most remote parts of the ocean. The growth rate is what gets me. 2 to 5 millimeters per million years. Think about that. In the time it takes you to grow a fingernail, a ferromanganese crust has not measurably thickened. In the time since the Roman Empire fell, a crust has grown by roughly 3 to 8 nanometers. In a human lifetime, it adds perhaps 150 to 400 nanometers, less than a wavelength of visible light. But over millions of years, layer by layer, atom by atom, these crusts build up into records that span the entire Cenozoic. A crust 20 millimeters thick has been growing for roughly 10 million years, and every atom that was present in the seawater during each millionth of those years is locked in the corresponding layer, heavy metals, rare earth elements, and interstellar debris. The specific crust that Knie used in 1999 was recovered from the Pacific Ocean floor. The crusts Wallner used in 2016 came from multiple locations. One of them, crust-1 in the paper, was a Pacific ferromanganese crust with enough depth resolution to see both the younger and older iron 60 pulses. The Eltanin sediment cores came from the Indian and Southern Oceans, recovered by the USNS Eltanin, which was a research vessel operated by the U.S. Military Sea Transportation Service for the National Science Foundation during the 1960s and 70s. These cores had been sitting in storage for decades. Wallner's team gained access to them and ran the iron extractions, and the iron 60 appeared in the expected time windows. There is something profound about the fact that the evidence was already in hand. The ocean crust samples had been dredged up years before anyone thought to look for interstellar isotopes. The Apollo lunar samples had been collected in 1969 and sat in Houston for almost 50 years before Fimiani dissolved them and found the iron 60. The Antarctic ice had been accumulating for millennia before coal drilled into it. The record was always there. The planet had been keeping a diary of its interactions with the galaxy. We just did not know how to read it. And reading it required one specific technology: accelerator mass spectrometry, AMS. Without AMS, this story does not exist. You cannot detect iron 60 at concentrations of 10 to the negative 15 using any conventional chemical analysis. You cannot distinguish iron 60 from iron 56 using a mass spectrometer that lacks sufficient resolving power at the higher mass range. You need to take individual iron atoms, strip them of their electrons, accelerate them to mega-electron-volt energies, pass them through a magnetic field to separate the masses, and then use a particle detector to identify each atom individually, one atom at a time. For weeks, the tandem accelerator at the Meyer-Leibniz laboratory in Garching, where Knie and Korschenegg did the original work, is a 14 megavolt machine. Atoms enter one end as negative ions, are accelerated toward a high-voltage terminal in the center, pass through a stripping canal where they lose multiple electrons and become highly charged positive ions, and then are accelerated again in the opposite direction by the same voltage. The double acceleration is what gives the tandem its name and its power. By the time an iron atom exits the tandem, it is moving fast enough that a magnetic field can separate iron 60 from iron 58 and iron 56 with the precision needed to count individual interstellar atoms. This is not a black box. It is not a simple instrument that produces a number. It is a cathedral of precision engineering and nuclear physics that requires a team of specialists to operate, calibrate, and interpret. And the fact that people built this machine and then thought to feed it a rock from the bottom of the ocean to look for atoms from a dead star is one of the most creative acts of scientific reasoning in modern history. I want to go back to the muons because I glossed over something earlier and I think the detail matters. I said that muons penetrate water to depths approaching 1 kilometre. I want to be more precise about why this matters for the extinction story. The key parameter is the muon's mean free path in water. A muon loses energy primarily through ionization as it passes through matter. The rate of energy loss depends on the muon's energy and the density of the material. In water, a muon with an energy of about 4 gigaelectron-volts can travel roughly 1 kilometre before it has lost enough energy to stop. At lower energies, the range is shorter. At higher energies, it is longer. But 4 gigaelectron-volts is squarely in the range of muon energies produced by the cosmic ray showers that Melott modelled for a supernova at 50 parsecs. What this means is that the radiation field from a nearby supernova does not respect the usual boundaries of Earth's biosphere. The surface of the Earth is protected by the ozone layer and the atmosphere. The deep ocean is protected by water. These are the shields that life relies on, and for most radiation sources, those shields work. Ultraviolet light is stopped by the ozone layer. Most cosmic rays are stopped or weakened by the atmosphere. Only the most energetic particles reach the surface, and their flux at sea level is too low to be biologically significant under normal conditions. But muons from a supernova cosmic ray shower bypass all of this. They are produced in the atmosphere, yes, but they are produced with enough energy to reach the surface and continue through water for hundreds of meters. The shield does not work. The ocean, which has been the refuge of marine life for billions of years, the safe haven where the largest and most complex marine ecosystems evolved, becomes transparent to the radiation for 100,000 years. And the organisms that lived at depths of a few hundred meters, the mesopelagic zone that we are only now beginning to understand the ecological importance of, were irradiated continuously for the equivalent of 5,000 human generations. Melott and his co-authors were explicit about the selectivity of this kill mechanism. Larger organisms absorb more radiation per unit time because they present a larger cross-section to the muon flux. The dose is proportional to the amount of tissue the muons pass through. A blue whale absorbs vastly more muon radiation than a sardine. A megalodon absorbed vastly more than a great white. The largest animals in the ocean were, by simple geometry, the most vulnerable. And the fossil record confirms this selectivity. The Plio-Pleistocene marine megafauna extinction was concentrated among the largest genera. Marine mammals were hardest hit, losing 55% of generic diversity, and marine mammals include the largest animals in the ocean. Sea turtles lost 43%. Seabirds, which spend much of their lives on or over the ocean surface, where UVB exposure would also be elevated, lost 35%. Sharks, whose body sizes span a wide range, lost 9% overall. But the losses were concentrated among the larger species. I have to be careful here not to overstate the case. Correlation is not causation. The marine megafauna extinction had multiple drivers. The closure of the Central American Seaway, which connected the Atlantic and Pacific Oceans until roughly 3 million years ago, reorganized global ocean circulation and disrupted the nutrient flows that supported Pliocene marine ecosystems. The onset of Northern Hemisphere glaciation changed sea levels, destroyed coastal habitats, and altered ocean temperatures. These factors alone could account for much of the extinction. What Melott's work adds is a mechanism that specifically targets large-bodied marine organisms. The other stresses, seaway closure and glaciation, are ecological pressures that affect all marine life roughly equally across body sizes. But muon radiation hits the biggest animals hardest. If you are looking for an explanation of why the Plio-Pleistocene extinction was concentrated among the megafauna, muon radiation from a nearby supernova is the only proposed mechanism that inherently predicts that pattern. This is the kind of result that makes you uncomfortable because it sits at the boundary between established and speculative. The physics is established. Supernovae produce cosmic rays. Cosmic rays produce muons. Muons penetrate water. Radiation damage scales with body size. The geological record is established. Iron 60 was deposited at 2.5 million years ago. The extinction happened at roughly the same time. What is speculative is the connection between them, the causal claim. And the causal claim may take decades to resolve definitively. But the Iron 60 does not go away while we wait. Let me tell you one more thing about the local bubble, because there is a dimension to this that Zucker's paper opened up and that I think has implications far beyond our solar system. When Zucker traced the motions of young stars on the bubble's surface backward in time, she found something that fundamentally changes how we understand star formation in our part of the galaxy. All 7 of the major nearby molecular cloud complexes sit on the bubble's surface, not near it. On it, they were swept up by the expanding shell of gas and compressed to the densities needed for gravitational collapse and star formation. This means that the supernovae that created the bubble did not just create a cavity, they created a generation of stars. And some of those stars are massive. Some of them are O and B type stars, the hot, luminous, short-lived stars that burn through their fuel in 10 to 20 million years and then explode, which means the bubble is seeding its own successors. The supernovae that created the bubble compressed gas into stars, some of which will become supernovae themselves, which will compress more gas into more stars. This is not a one-time event. It is a cycle, an ongoing, self-sustaining process of destruction and creation that has been running in the galactic disk for billions of years. The local bubble is not unique. The galaxy is filled with similar structures, overlapping and intersecting, each one carved by a chain of supernovae, each one triggering star formation on its surface, each one feeding the next cycle. The technical term for this is supershell propagated star formation, and it means that the galaxy is not a static backdrop against which life plays out. The galaxy is a dynamical system, constantly reconfiguring itself through violence, constantly creating the conditions for new stars and new planets, and potentially new biology. The iron 60 on the ocean floor is not a footnote in this process. It is the calling card. It is the galaxy saying, in the only language it knows, that it was here, that it did something, that its influence extends all the way down to the atoms in the deep ocean of a small rocky planet orbiting a middle-aged star that happened to wander into the blast zone 5 million years ago. I want to say something about the emotional register of this story, because I have been feeling something while writing it, and I think it is worth naming. It is not fear. The probability of a nearby supernova in any given human lifetime is negligibly small. There is no actionable threat here, nothing to prepare for, nothing to worry about. What I feel is something closer to vertigo, the sensation of suddenly seeing the scale of the thing you are inside, like standing at the edge of a cliff you did not know was there. You are not going to fall. You are safe. But the drop is real, and now you can see it, and you cannot unsee it. You live inside a cavity made of dead stars. The debris from those stars is in your ocean. It is on your moon. It is falling on your ice right now. The radiation from one of those stars may have contributed to the extinction of a third of the large animals in your ocean. And the cavity itself, the structure you live in, is still expanding, still growing, still pushing gas outward, still creating new stars, still preparing the conditions for the next round of explosions. The galaxy is not done with this planet. It has never been done with this planet, and the record of its attention is written on the ocean floor, in atoms that should not be there, counted one by people who spent weeks in front of accelerators waiting for a single click. I started this by telling you that radioactive iron from a dead star is falling on Antarctica right now. I want to end by telling you what that means. It means the story is not over. It means the transcript is still being written. It means that somewhere in the geological record of the future, in a layer of ferromanganese crust that has not yet begun to form, or in a column of ice that has not yet frozen, there will be atoms from events that have not yet happened, supernovae that have not yet detonated, neutron star mergers that have not yet collided, violence that has not yet occurred. The ocean floor will catch them. The ice will catch them. The moon will catch them. And if anyone is here to look, they will find them. Because the galaxy always leaves a record, and the record always ends up in the rock. The debris is not ancient history. It is current events. The last iron 60 atom to land on Earth arrived sometime in the past few years. The next one will arrive sometime in the next few years. And between those two atoms, between one click of an accelerator detector and the next, an entire human life could pass. Born, lived, and died on a planet that was being quietly marked by a dead star that it never knew existed. You have been living inside this story your whole life. The evidence was always there. In the crust, beneath the ocean, in the soil, on the moon, in the ice at the poles, in the thin, hot gas surrounding your solar system. The atoms were there before you were born. They will be there after you are gone. They are the galaxy's handwriting. And the message, if you read it honestly, is not a reassurance. The message is that you are not separate from this. You never were. The same processes that forge iron in the cores of stars and scatter it across light years and deposit it on ocean floors, those processes shaped the planet you stand on, the atmosphere you breathe, the climate that built the world you know, and possibly the evolutionary pressures that produced the species you belong to. You are not watching the universe. You are inside it, and it is not finished with you. There is one final thing I want to leave with you, and it is the thing that I keep coming back to when I try to sleep after reading these papers. When Zucker mapped the local bubble, she found that the sun is near the center, not at the center, near it. The sun's galactic orbit did not carry it perfectly through the middle of the cavity. It entered from one side roughly 5 million years ago, and it has been drifting through the interior ever since. It will eventually exit through the other side. In a few million years, the sun will leave the bubble and enter denser interstellar medium again. But for now, we are inside. And being inside the bubble means we are in a region of space that is, counterintuitively, more exposed than the average location in the galaxy. The bubble's interior is thin. The gas density is 1/100th of what it is outside the walls, which means the heliosphere, the sun's protective magnetic bubble, is actually larger than it would be in denser interstellar medium. In a denser region, the interstellar pressure compresses the heliosphere. Inside the local bubble, the heliosphere can expand further because there is less external pressure to resist it. That sounds like good news. A bigger heliosphere means a larger shield, but it also means the shielding is thinner. The magnetic field per unit volume is weaker, and when a cosmic ray surge hits, when the debris from a supernova inside the bubble arrives, there is less interstellar material between the source and the sun to slow it down. The cosmic rays have a relatively clear path from the supernova to Earth. They do not have to plow through dense interstellar gas. They are already in the cavity, and the cavity walls bounce them back. This is the geometry of vulnerability. We are inside a shelter that was built by violence, and that, in certain specific scenarios involving additional violence within the shelter, provides less protection than the open galaxy would. The local bubble is a cleared area, and a cleared area, while normally quiet, becomes extraordinarily dangerous when the threat is already inside. The 2.5 million year supernova was inside the bubble. The cosmic rays did not have to cross the bubble walls. They did not have to penetrate dense interstellar medium. They were generated inside the cavity, and they stayed inside the cavity, bouncing off the walls for 100,000 years, bathing everything within 1,000 light years in elevated radiation, including Earth. If the same supernova had occurred at the same distance but outside the bubble, in the dense interstellar medium, the cosmic ray flux at Earth would have been significantly lower. The interstellar material would have absorbed and scattered and slowed the particles. The magnetic fields in the denser gas would have deflected them. The bombardment would have been weaker and shorter. The bubble, the structure that was carved for us by dead stars, the cavity that has been our galactic home for 5 million years, the thing that every pop science article describes as a cosmic cocoon or protective shell, actually made the supernova's effects worse. The shelter amplified the threat. Think about that. 15 stars died over 14 million years and carved a bubble 1,000 light years across. The sun drifted into it, and then another star, perhaps the 16th, died inside the bubble, and the bubble's walls trapped its cosmic rays and reflected them back onto everything inside, including Earth, for 100,000 years. The structure that was supposed to be our home became the walls of our radiation chamber, and we are still inside it. I keep coming back to the word Wallner used, coincidence, an interesting coincidence. 2 supernova pulses in the geological record, 2 major transitions in Earth's climate and biology, the Plio-Pleistocene boundary and the marine megafauna extinction, the late Miocene turnover, and a bubble carved by dead stars that the sun wandered into just before all of this happened. Wallner was being careful. He had to be. He is a nuclear physicist publishing in Nature, not a commentator offering opinions. But the data he uncovered does not require his caution. The data can speak for itself. And what the data says is that the galaxy has been intervening in the story of life on Earth for as long as the record extends. Not through conspiracy, not through intent, through physics, through the ordinary, inevitable, violent life cycle of massive stars. Stars die. When they die, they explode. When they explode, they scatter debris. Some of that debris reaches Earth. Some of it is radioactive. Some of it carries elements that should not exist on this planet. Some of it brings cosmic rays that strip the ozone and irradiate the ocean. Some of it triggers extinctions. Some of it may trigger new evolutionary trajectories. And all of it settles, eventually, onto the surfaces of whatever planets and moons happen to be in the way. The iron is in the crust. The plutonium is in the rock. The signal is in the ice. The cavity is all around us. And the next atom of iron, 60 to arrive from interstellar space, an atom forged in a star that died millions of years ago. An atom that has been drifting through a bubble carved by 15 explosions. An atom that will cross the heliopause and drift through the solar system and enter Earth's atmosphere and fall silently onto whatever surface it encounters. That atom is on its way right now. It does not know what it will land on. It does not care. It is following the physics, and the physics does not stop. The ocean floor remembers, the moon remembers, the ice remembers, and now, so do you.